So welcome back. Happy Friday. We left off talking about this really cool result. I think it's pretty cool, that connects the autocorrelation of a time domain signal with its power spectral density or energy spectral density. So it's a way to get from the time domain to the frequency domain without actually having a closed form expression for the signal. And that's really where the power of this comes out. So before I continue on into the slide set, does anyone have any questions? Okay, fair warning, problem set 1 has been posted. So if you're looking to work on that, go for it. I'm trying out a thing where I think there are 5 questions on this week's problem set. And if you're an undergrad, I'm only going to ask you to do the first 4. But if you're a master's student, I would like you to do the 5th one as well. So just to make sure that the master's students are getting their money's worth. You can thank me later, it's fine. Okay, so let's go over to desktop number 2. There we go. Okay, so just to recap, we had this relationship that if I take the Fourier transform of the autocorrelation, I get the energy spectral density. Now that same statement is true if I take the Fourier transform of the autocorrelation of a power signal. It's just you have to adapt it to mean that you'll get the power spectral density. And so the application, the immediate application of this is we get to talk about the spectrum of a random signal. And this is, I'll be honest, this is pretty fundamental to the rest of the course. So let's take our time with it. First things first, can I take the Fourier transform of a random signal? Like by definition, can I plop it into an integral and take the integral?
Probably not.
Now, what would you put in the integral? There's no expression, right? Because the value of the signal is random at any given time. So it would be like you might have statistics on it, you might have the density, but you can't actually take the Fourier transform by definition, by the integral definition, if you have a random signal. Yet, I want everyone to want there to be a way to spectrally talk about a random time signal. Right? There should be a way that if something is random in time but kind of slowly varying, it should have spectral content near DC. If something is randomly varying but kind of frequently randomly varying, then it should have higher frequency components. Right? So we should be able to, in some way, talk about the spectral content of random signals. In fact, we can, and the key is this autocorrelation. So let's set up the problem a little bit. Let's say we've got an infinite string of bits. We've got a whole mess of bits that we need to get from here to there. And we have encoded those bits as what's called a bipolar return to 0 line coding. Okay, yikes. Do you understand what I mean in this first bullet point? If a discrete time signal, D, at a time value n, is a Bernoulli random variable. Okay, and then just since there's no n's over here, every D of n is its own independent Bernoulli random variable. And remember, Bernoulli is all about coin flips. So these are 50-50 coin flips. So the nth bit is 50-50 going to be a 0 or 1. That's all I'm saying. And then, so take that string of bits, so 0, 0, 1, 0, whatever it happens to be. And then if you get a 1 bit, map that to a positive rectangle. If you get a 0 bit, map that to a negative rectangle. So if this is our D of n signal, then our x of t signal would be, well, it would be a -1 for the bit period t sub b. And then it would be another -1 for the second bit period. And then it would be a +1 for the third bit period. And then it would be a -1 for the fourth bit period. Okay. So, but again, these are random. I'm not saying that this is exactly what the signal would look like, but if we were to pause the bit stream and come across 0010, then the waveform would look -1 for 2 bit periods, +1 for 1 bit period, and then -1 for the fourth bit period. That's not true. Oh, good start, Clay. Good start. No, because it's what I just drew is what's called a non-return to zero. But I told you that this should be a return to zero. And primarily it's because I neglected this guy. So let's start over. I'm sorry. Okay, so if we encode these with a return to zero line coding, then a 0 bit means we go -1 for half the bit period and then return to 0 for the second half. All right, and then we get another 0, so we go back to -1, half a bit, back to 0 for the second half. Okay, so this is t sub b. This is 2t sub b. And then if we come across a +1 bit, we go up and then back to 0. And then we go negative. Okay, now we're cooking. So this is still 4t sub b. All right, did I get that right? I think so. So this is an example of what x of t might look like, but it is not what x of t is, right? Because x of t actually depends on a random variable outcome, many random variable outcomes. And so if your instinct when I ask you about the spectrum of this signal is to try and take the Fourier series of this thing that I've drawn, that's not what I want. What I want you to think about now is, because we've got a random signal in our hands, think about how we could describe the autocorrelation of this signal. So what would it mean? Let's make this plot a little bit bigger.
I have a quick question.
Go ahead.
Does T sub B, what does that stand for necessarily? It's just the time between each D of n, like D of n, what am I trying to, D of n, it's like between 0 and 0, 0 and 1. Is that the time between that? What is,
yeah, so the reason I use T sub B is it's the bit period.
Oh, okay.
So it's the period of time that we're going to use to send each bit.
Okay. It doesn't correlate to the output of D of n, or will that correlate?
No. So whatever D of n is, that number will be either a 1 or a 0, and that will then get mapped to a waveform that lasts between n TB and n plus 1 TB.
Okay, that makes sense. Thank you.
Yeah, so if you like, we could also put another row here. This would be n equals 0, 1, 2, 3. And now I think, now we have a discrete time index n, we have a bit that corresponds to that, d of n, and then we have a waveform, or sometimes called a line code, L-I-N-E, that takes the bit and maps it to, like, say, a voltage that you could actually measure on an oscilloscope. Okay, so let's make that picture a little bit bigger. And I'm going to plot just this representative sample. Okay, so what can we do here is we can label this as the time axis, but I'm going to use tau for reasons that I hope will become clear in a moment. And this is then in blue, this is x of tau, or this is what x of tau might look like. And then if I come along, and if I want to talk about autocorrelation, then I have to talk about copying x and shifting it. So then we could also talk about copying, taking the same blue waveform and shifting it by some amount of time, which I'm going to call little t. So shift it over. Oh, you know what would be cool is if I could copy paste this, and then that would be way faster. I don't know if I could change the color then. Okay, so in blue we have x of tau, and in green we have x of tau delayed by what I'm going to call t. So that means that this is tau equals t in Raspberry there. So the autocorrelation, well, that's a question. We have two different forms of autocorrelation. We have autocorrelation for energy signals. We have autocorrelation for power signals. And I would like your input. Is the random signal x of t an energy signal or a power signal?
Power signal.
You're correct. Can you explain why?
Because it's just not finite in time.
Good. It's not finite in time, and also it's everlasting. I guess that's exactly what not finite time means, is if you were to square x, even if it were all 0 bits, then squaring those rectangles would make them all positive, and you'd have an infinite amount of area, which you could then divide by the length of time that you were running it for, and you get a finite power. Exactly right. So since x is a power signal, it's a random signal, but it's also a power signal, we should use the power form of autocorrelation. So that is r sub xx of t looks like the limit as the big T goes to infinity of some interval of length big T, any interval that is, of x of tau times x of tau minus little t conjugate. But since x of t is real, I'm going to forget the conjugate here. Integrate over tau. Okay, so at least we have the right form of the autocorrelation function. The next trick is not to write this in terms of some arbitrary capital T, but rather only consider this in chunks of TB. And so one way to do that would be to flip the, or to change the variable in the limit here. So let's take the limit as n goes to infinity. And we're going to then integrate over n times the bit period. Okay, and the integrand stays the same. Okay, so now all we have to do is check what happens when we slide x of tau minus t relative to x of tau. So the question so far?
This might not be important. I was just wondering, I don't want to go off on something. I was just wondering when to stop at TB based on D of n. So you have this length of TB divided by 2 that defines whether it's 1 or -1. How do we know that it's 0 just for up to TB before it hits the next the Bernoulli data between it?
So imagine that you are the part of this circuit so there's some kind of system sitting somewhere, and into this system comes a bit, and out of this system comes a voltage. Now inside this system, sorry, I don't want to draw another arrow there. This system, the thing that characterizes this system is the bit period. Okay.
Okay. So
another way to say that is that you will only be given a bit every TB seconds.
Okay, so I should just assume that in some sense when it comes to
every TB seconds.
Okay.
Okay, so yeah, you'd have to then, this system would have to be matched with the bit source that could only give you a bit every TB seconds. Or you could run a buffer and then siphon off that buffer every TB seconds or something like that.
Okay, that makes sense.
Cool.
Thank you.
Okay, so there are a couple cases that we should consider. So when little t is between 0 and half the bit period. Now what's going to happen here? So if the shift is to the right, but by less than half the bit period, is the product of x with the shifted version of x ever going to go negative?
No.
No, because you will either get kind of non-zero times 0 stuff, or you will get -1 times -1, or +1 times +1. And so the result will always be positive.
One question. Could it actually, if you shift it far enough, I guess?
If you shift it far enough, but I'm restricting us to only talk about within half a bit period.
That makes sense. Thank you.
Yeah, sure. So in this case, this means that each TB contributes how much area? Contributes. And I'm talking about area under the product, x of tau with x of tau minus t. Well, it's a height of 1, and it's a width of, I think it's TB over 2 minus t. So it's a height of 1, and the width is TB over 2 minus a shift. Anyone need help interpreting that, or need me to explain that in a different way? So remember, this is TB over 2. Now, since every every chunk of TB seconds on the tau axis contains 1 bit, and regardless if that bit was positive or negative, then the areas are going to flip to positive, and the width we're looking at is the distance between TB over 2 and T. So this area is what I just calculated, and that area is repeated in every chunk of TB, every chunk of width TB in the tau axis. All right, I'm going to proceed, assuming that we're all good with that. When T is exactly TB over 2, how much area is there?
Zero.
Yeah, there's no area because any overlap is of negligible width. And here is the special sauce. Here is how we're going to capitalize on the distribution that we were told. If T is bigger than TB over 2, tell me, if I am sitting in this bit stream, say I am this 0 bit, what's the chance that the next bit is a 0?
50%.
What's the chance the next bit is a 1?
50%.
So half the time, when I get shifted onto that bit's period, I'll contribute positive area. The other half the time, when I get shifted onto that bit, there will be negative area contributed. And that is true over every single bit period. Okay, so once I shift beyond my own bit period, I have an equal chance, a 50-50 chance of contributing positive area to this integral as negative area to this integral. And that's true for every single bit in the stream. So we have a 50-50 chance of positive area versus negative area. And since we're considering overall time, since we're letting big N go to infinity, then the net contribution of all of these regions is 0. Let me quickly check what's on the next slide here. Oh, this would have been a little bit more room, but we can write the conclusion here. So this is going to be the limit as n goes to infinity. No, I think I'm actually using the limit in my argument that the rest of the area goes away. So I think I'm going to lose the limit. This is going to be one of two things. It's either going to be 1 over n times TB times n bit periods. Each bit period contributes TB over 2 minus T area. And that's only true if we're looking at little t's within half a bit period. Otherwise, the autocorrelation is 0. So let's make sure we understand where every one of these terms came from. The first one's easy. It's right here. And the last one's easy because it's what we had on the previous slide. This was the area per bit period. And then that leaves this as the number of bit periods. Cool. Questions on that? Now I threw those at.
I have a question.
Go ahead, Ricardo.
So this analysis we went through works for the return to zero line coding. Does it work for non-return to zero line coding? It might not.
I'm trying to think. I think it would. I think that the width of each of this integral would have to be probably TB instead of TB over 2.
Okay.
I think. It becomes a little harder because the amount that you leak from one bit period to the next will either be, like immediately, it will either be positive or negative. But I think it's equally likely to be either one. Yeah. Okay. Yeah, so the key to this whole thing was the IID, the independent and identically distributed nature of the bits. If you somehow have correlation between bits over time, then my claim that all the areas wash out, that's no longer true. Okay, so if you buy what I just wrote, then we can plot this in the time domain. So this is the autocorrelation of a random bit string. And
I have a question.
Go for it.
Sorry if this sounds dumb, but how is it that those two ends don't cancel out for number of bit periods?
They absolutely do, right? I'm counting on it.
Okay.
Yeah.
Okay, cool.
Yeah.
I mean,
You're
I was
ahead of
just
me,
wondering
that's
if that mattered or not. Okay, thanks.
Yeah. And in fact, then I distribute the 1 over TB in as well. And so this function peaks at 1/2, and it drops linearly in both directions until you get to TB over 2. I thought someone was going to ask about the absolute values. They literally came out of nowhere. But if you go back to the previous slide and end up shifting in the other direction, you get the exact same result. Or you could say that you know that autocorrelation functions are always even. And so if you solve for them in positive time, you just get to mirror them into negative time. That's another handy result, if the signal's real. Okay, so let's confirm that this matches what intuition tells us should be true. This says that if I take this return to zero code, waveform, voltage if you like, and I shift it, then it starts to look less and less similar like its unshifted version, right? That's this diminishing slope in both directions. Until eventually, if I shift it by at least half a bit period, there ends up being no net similarity between the shifted version and the original version. And that's principally because now what bit every bit is landing on is 50-50 same bit or opposite bit, which means that overall, if we're looking at the area under the entire product, we get 0. Said another way, if you were tracking this x of t voltage and your timing got off, then your estimate about what bit is truly being sent at that given time, if your timing gets off by more than TB over 2, you have no idea what bit was sent. Right? Because if you're looking at a shifted version of the, like if your timing gets off, if you're looking at a shifted version of the received signal, and that lag exceeds half a bit period, you might as well be throwing darts. Because every bit is not correlated with the last bit or the next bit. Okay, those are two different interpretations of this kind of triangular going to zero type graph. But the payoff, the real point of this is, look, we have an autocorrelation. We have an autocorrelation that doesn't depend on anything random. We have a concrete closed form deterministic expression for the autocorrelation. It's piecewise, sure, but it's deterministic. In fact, it's also in your Fourier tables. So if I Fourier transform this, actually, does anyone know what we get when you Fourier transform a finite duration triangle?
Sinc squared.
Sinc squared, good. Right, because this triangle is like what would happen if you convolved two rectangles. So you should have then multiply the Fourier transform of a rectangle. So you get 2 sinc times sinc, which is sinc squared. Okay, so at the end of the day, we get the power spectral density is, and there's some scaling factors, but yeah, the main idea is that this is going to be a sinc squared. Awesome. Questions on this? I hope you see that this has immediate ramifications. That now we can start talking about, if I want to send bits, I have to map them to voltages. And those voltages, that signal, even though the content of the signal is random, that signal still has a spectrum, which means I can still predict how filters will treat it or how it will pass through filters. Okay, so this is, I don't want to overstate it, but this is important. All right. And then if you like, there's, I think here's some MATLAB code to talk about the bandwidth. Oh yeah, that's right. The original question 2 slides ago, 45 minutes ago, was what's the bandwidth of this signal? And the idea was that to answer that, we should have a look at its spectrum. We want to look at its power spectrum, and that's what we just derived. S sub x of f is the power spectrum of this waveform. And so it's not a finite bandwidth signal because the sinc squared goes on. It has tails that go on forever. However, it is essentially band limited. That is, there is a point on the frequency scale, frequency axis, inside of which we have 90% of the power. Ricardo, was there a question?
Yeah.
Go ahead.
We derived the spectrum density of the bit signal, but we can't really transmit bits since they're DC components. How are we going to, is this still going to apply when you actually try to transmit the signal? Is the distribution going to look similar?
Sure. So yeah, I should be more careful that what we analyzed was the autocorrelation of the X signal, which is a continuous time signal. And as long as you're not transmitting this over radio frequencies, right? If you're doing this over, say, wired communication, then there's nothing stopping you from switching this voltage from 1 to 0 to -1 to 0 to -1 again, back to 0. So you could do that. And what this analysis would tell you is if you knew the properties, if you knew the spectral properties of the wire that you were trying to send this data down, then you could predict how deformed the resulting received signal would be.
Gotcha. No, I get it.
Cool.
Yeah, thanks. I'm just used to sending things over the air.
So, I mean, there's nothing stopping us from taking this line code, which is very boxy, and modulating it with a carrier.
Right.
Okay, so then you would have to say, okay, if I multiply two signals in the time domain, what do I do to their autocorrelations, and then what do I do to their power spectral densities? But yeah, we're going to get there. Good point.
Thanks.
Okay, so this is just to remind you that there is such a thing as essentially band limited versus strictly band limited. That is, there is no point on this frequency axis where I can say after this point, there's no more power, but there is a point on this frequency axis that I can say within this band, most of the power lies. Okay, and that's the difference between strictly band limited and essentially band limited. I also hope that you see that depending on the line code that we chose, the shape of this would change. Yeah, so if we did return to 0, then maybe, so if we had done a return to 0 line code, then my gut says that we would get a wider triangle where this goes to TB instead of TB over 2. If we did return to 0. And if something is wider in time domain, it actually becomes narrow in frequency domain. So maybe this sync would have a narrower essential bandwidth, which means that you could pass it through a more lossy channel, or a longer wire, if you like, that has a more low pass characteristic, and you would get more of your data through. There's no free lunch, of course. Then if you do a non-return to 0, your timing becomes very difficult to recover, especially if you have a sequence of many consecutive equal bits. Right? Then your receiver is seeing literally DC for a long time, and it's hard for the receiver, in case there's any leakage in its timing, to reset the timing. Whereas if every bit returns to 0, then every bit on your receiver, you can reset your phase counter, if you like. Okay, that's not part of this problem, but it is an interesting thing to consider, is that this idea behind trade-offs between spectral characteristics that we like and timing characteristics that we like, there's no getting around it. Okay, so I think we can close with this quick analysis, which is if I'm going to be talking about things in terms of their power spectral densities, which is now easier for us to talk about than their Fourier transforms directly, then we should look into how power spectral densities are affected by LTI systems. Okay, so we know that Y of F, the output of this system, is X of F times H of F. And we also showed that the power spectral density is the Fourier transform of the autocorrelation of Y. The power spectral density has another property, so S sub Y of F. Remember, we defined it as the magnitude squared of the Fourier transform. Another way to write magnitude squared is take the number, or in this case the function, and multiply it by its complex conjugate. Sorry, that's an F. Okay, but we have an expression for Y of F, which means we have an expression for its conjugate. So we get x of f, h of f times x conjugate h conjugate. Then these two give me the power spectrum of the input. And then the h's, if we assume h of t is real valued, then we get this conjugate symmetry. We get h of f magnitude squared. Okay, this is not earth-shattering. This is actually probably what you expected, is if Fourier, you get to multiply things in the frequency domain, you also get to multiply quote-unquote power spectra, where this is not technically a power spectrum. It is just, because we talk about power spectra of signals, and this is kind of characteristic of a system. But long story short, if the system is a low-pass system, then we're going to only pass the low part of the power spectrum through. If the system is band-pass, then we're only going to pass that band of the power spectrum through, right? So don't expect your jaws to drop after this, but it is nice to know that the things that we like filters to do are done to power spectra just as they're done to regular spectra. All right, that exhausts our slide set for this module, which means that we are ready to move on to the next module, which I think we can do on Monday. I'll stick around here for questions, but otherwise, I hope you have a nice weekend.